Molim. So, hello, good morning, everybody. I hope you can hear me. My name is Željko Bačić, as you can see on the slide, and I will start this training which we have organized in frame of the EPOgio project. I'm very glad that you have joined us after quite short announcement, but I hope that training which we have prepared will respond to your interest and expectations which you have about respond on disasters, especially earthquakes, catastrophic earthquakes, which can be provided by geoscientists with focus on surface displacement. Namely, as we all know, in a case of natural disasters like strong earthquakes there are very many aspects where geoscientists can provide additional support to the services and citizens. So in this sense, we have limited ourselves just on the specific aspect of surface displacement. I will share my screen now and start my presentation. No, something's wrong. Can you see my slide, please?
Not yet.
Not yet.
Just a second. I have to turn on my... Yes, now it's better. Okay, so I will give you in the first 45 minutes introduction to the topic and why, so explain why we have prepared this training and what are the aspects which were driving us to do it. I have to say honestly, the earthquakes, especially strong earthquakes, they have, of course, terrible consequences on the people's regions which are hit by the earthquakes. But from the perspective of science, earthquakes as such or appearance of the earthquake presents also opportunity for research, opportunity for investigations, and this was also case which so the earthquakes which happened in Croatia were the reasons for us to research on this topic. So this training is provided in frame of EO4Geo project. EO4Geo is abbreviation for the title towards an innovative strategy for skills development, capacity building in the space geoinformation sector, supporting Copernicus user uptake. So this is a specific Erasmus project, Sector Skills Alliance project, and you can see that this is a 4-year project which should end with this year, so end of this year. And it's a huge project in a sense that it were 26 partners in the consortia and 22 associated partners from various various profiles, so academic institutions, companies, networks, associations, and of course somewhere behind this consortium and which gathered together was also the Copernicus Academy network. So because the focus of the project is on a Copernicus program of European Union. The project has challenges, so should help bridging the skills gap between supply and demand of education and training in space geospatial sector. So we are aware that academic sector is has problems with modernization of the content of its curricula, because the changes are happening so fast and the processes of changing of curricula are not so fast. So there is a gap which then reflects on the business and public sector, which are not receiving new professionals with the skills and knowledges they demand in some very moment. So the idea of the project is to work in a multi and interdisciplinary way and to apply innovative solutions for education. The education and training actions which will be developed, which will be case-based and various collaborative learning scenarios, including many present forms today, but also looking to develop some new. And also the project should define a long-term and sustainable strategy of filling the gap between the supply and demand for space geospatial education and training, and taking into account not only current but also expected technological and non-technological development in the space geospatial sector. To achieve this, project has a lot of activities. So first, there is creation and maintenance of ontology-based body of knowledge for the space geospatial sector. Then to develop an integrated dynamic collaborative platform which will enable all interested parties to benefit from the project results. Designing and developing a series of curricula and portfolio of training modules which will be usable in context of Copernicus to broad societies, so to other academic institution professionals, etc. And conducting a series of training actions for a selected set of scenarios in the three subsectors, so integrated applications, smart cities, and climate changes. So we can say this training is maybe a little bit specific, but it falls under the integrated application. And the long-term action plan will be developed and endorsed to roll out and sustain the proposed solutions, so to ensure sustainability of projects, of the deliverables of the project. As you can, here are the members of the consortia, so you can see that they are coming from 16 European EU countries, and the coordinator is GISIC from Italy. Together with, so the main coordinator is GISIC, but then there are also three other coordinators which are coordinating certain parts of the project. These are Catholic University Leuven, Plus from Austria, and UGI from Spain. About the webinar, so we called him a fast disaster response, satellite technologies for surface displacement monitoring. And what we will talk today in coming 2 days is about the usage of Earth observation and global navigation satellite systems supported by GIS technologies for fast disaster response with emphasis on surface displacement monitoring and delivery of computed information, so calculated information to the public. The webinar will include the theory and practice about InSAR and GNSS technology, and we so to say targets geo-professionals and researchers, so not while somebody persons who are informed and have certain pre-knowledge about the topic, who are interested in disaster risk reduction and management of catastrophic events. The webinar is organized by Faculty of Geodesy of University of Zagreb, EPOgio team. So basically, we are also a partner on the EPOgio project. And we combine it, so it's done in collaboration with three other Erasmus Plus projects, GeoBiz, SEED4NA and UN4DRR, which I will explain a little bit about those projects and why we have done it. And of course, it's open to everybody. So the GeoBeast project, like two other projects, is a capacity building for higher education Erasmus Plus project, and GeoBeast is abbreviation for business-driven problem-based learning for academic excellence in geoinformatics. And the focus of the GeoBeast project is basically the fact that technology is developing so fast, so that academic institutions have problem in catching with those changes, catching problem to modernize the curricula, especially in the geo studies, which are today very much technology driven. So what we want to do is in cooperation with businesses, so through the business academia cooperation, we want to modernize the practical part of technologically driven courses in field of geo studies. And the project is focused on Western Balkans, so countries, Albania, Bosnia-Herzegovina, Kosovo, and Montenegro, and Moldova, while the program partners are beside the Faculty of Geodesy from Zagreb, we are the coordinators of this project. Partners are also coming from Belgium, Germany, and Serbia. And this project is also if I may say so, interesting because it combines academic institutions. Partners are academic institutions and private companies. SEED4NA is a project in North Africa, so SDI and Earth Observation, Education and Training for North Africa, involving partners from Algeria, Egypt, Morocco, and Tunis. Coordinator is a team from Catholic University from Leuven. And also partners are coming from Germany, the Netherlands, Sweden, and Croatia. And this project is focused on raising capacities of academic institutions in Northern Africa regarding SDI, spatial data infrastructure, and Earth observation to foster development of SDI in those African countries and foster better use of Earth observation. And the last project is University Network for Disaster Risk Reduction and Management in Indian Ocean Rim, involving Indonesian universities from Indonesia, Maldives, and Sri Lanka. And the coordinator is coming also from Belgium, but Free University Brussels. And partners are also coming from Spain, Cyprus, and the University of Zagreb. So our team is also involved in this project. So what is common to all those three projects and why we have, so to say, prepared this training in collaboration with the projects is the fact that all three regions are in seismically active zones and are frequently facing earthquakes. So in this sense, this is a part of the, so to say, activities of the academic institutions, part in a sense that from all those countries, partner academic institutions are from time to time in situation to face the strong earthquakes, even catastrophic earthquakes or other natural disasters, and are in position to act and support the rescue and recovery activities. So today's presenters are Dr. Marian Grgic. He is a postdoctoral researcher at the Chair of State Survey here at the Faculty of Geodesy, and his areas of interest are related to gravimetry, magnetometry, physical geodesy, as such, state surveys. So all technologies which are very much related also to the seismology or to surface displacement as such. Then second speaker is Assistant Professor Daniel Sugar. He is coming from the chair of satellite geodesy, and he is a specialist in GNSS technologies, and also in this sense computation of the displacements by usage of permanent GNSS networks. And myself, I'm professor at the chair of satellite geodesy and involved in originally in GNSS technology. So this is my original background, but today involved in sensor integration and navigation, Earth observation, SDI, so quite a number of fields. So we will in these 3 days present you, deliver presentations and the practical examples which we have prepared. So let me go to the topic, and our topic are catastrophic earthquakes, or we can expand this any natural disaster with catastrophic consequences, and because the, so to say, the technology and activities which we will elaborate are not only focused on the earthquakes. Earthquakes are used as a, so to say, example, but it can be also used for other natural disasters. And the only common thing, or only, so to say, granted thing, considering the natural disasters, is that they are occurring frequently worldwide. So in this sense, what we can say, unfortunately, is that we can count that some natural disaster will happen sooner or later. The triggers for our research were two events, not only many earthquakes, but the two main earthquakes which happened on March 22nd last year, early in the morning in Zagreb. So it was just 7 kilometers of Zagreb center. So basically in a Zagreb urban area was epicenter, and very shallow earthquake, just hypocenter was on 10 kilometers depth and with magnitude 5.5 on Richter scale. There was luckily only one human loss, but 30,000 buildings are damaged to the level that they require reconstruction. Here are some pictures from this earthquake, so you can see that there was a lot of damage, not, to be honest, not ultimately devastating in a sense that buildings collapsed, but as you can see, many roofs, many walls broke down. Even the one of the now I'm missing English word. One of the towers of the Zagreb Cathedral also broke down, and the cathedral alone was quite demolished. This earthquake, what I think this is important to say, happened after 140 years since last devastating earthquake which hit Zagreb. So we, in this sense, we forgot what does earthquake or heavy earthquake, strong earthquake means. It was a it was a very big shock. This earthquake, it was also early in the morning, so most of the people were sleeping, and it was unfortunately also very cold day. So although it was almost end of March, at that day, also there was some snowfalls in Zagreb, so which complicated the rescue activities additionally. Just 9 months later, on December 28th and 29th, two strong earthquakes hit region of Banja. The location of the epicenters was vicinity of town of Petrinja. And what was also, it happens, but it's not so frequent, is that first earthquake, which was on 28th December, was in fact weaker, and the second one day after was stronger. So it was a 6.2 on Richter scale, and 7 people unfortunately died in the earthquake, and you can see that double number of buildings is damaged, but this time much harder. So there was many buildings are completely demolished, so unusable for living or even for any standard reconstruction. So many of the buildings in Petrinja and surrounding have to be completely demolished and rebuilt newly. So those two, the earthquakes as such, we all know that they cause damages. We saw it. They cause human losses. Well, if we look statistics of strong earthquakes, the human losses in those two earthquakes were not so big. There are earthquakes which take much more lives, but it's also, so to say, depends very much on the frequency of such events. So also earthquake in Petrinja in this region was after some 105, 115, sorry, years when previous strong earthquake hit this area, which is not far away from Zagreb, just to say. So basically, in Zagreb, we are shaking each time when there is a little bit stronger earthquake in Petrinja region. Of course, earthquakes are causing panic, fear, shock as such, and humanitarian crisis like this picture from the Zagreb Central Maternity Ward, where basically all mothers with young babies basically went out from the hospital and were standing for a while on the freezing temperature because it was very cold on this day. So a lot of problems appear, and of course such earthquakes are causing a lack of goods, so the chains of supply are broken for a while and or not functioning for a while, and many things are then missing in the very moments after the earthquake, hours and days. Of course, different things are necessary in first hours and some other things later. Those earthquakes require a fast reaction. Of course, first from rescue teams, from various city and state services, electricity, gas line, telecommunications, whatever. Of course, police, considering this overall security, communication services, so informing the citizens, but informing also globally about the event and the situation. And in many situations, or most situations, when catastrophic earthquakes appears, then also military is activated to help in rescue and recovery activities. We know also that all countries are aware of this jeopardy or threat, and more or less all countries in the world have developed civil protection plans and established services which are prepared to act in case of such emergencies. But in case of catastrophic earthquakes, we can say that regardless to the level of civil protection organization and available resources in some region or country to conduct the rescue and recovery activities, in principle, those capacities are not sufficient. So they are in the very moment after the earthquake, they are overloaded, they are simply insufficient. Nobody can prepare such a volume of and capacity of those organizations to be ready for such events. So basically, what I'm trying to say is that in such cases, support usually is needed from everybody who can and is ready to offer it. So we know in such cases, basically whole nations are mobilized to support those regions which are hit by earthquakes. Another issue, very important issue or very relevant issue is the state of the people who are affected by the earthquake. Fear and panic are, so to say, natural states of the people's mind in case of such earthquakes. And I can tell you that in Zagreb and in Petrinja and surrounding towns, we are, even after more than 1 year after those first earthquake, today, if somebody is just shaking a table with his leg, that most of the people in Zagreb and Petrinja region are automatically thinking, is it an earthquake? So this has quite a long reflections on people and on our behavior. So when we speak about the panic and fear, in the very first minute, it's a shock. Of course, it's basically a panic, which then after a few minutes or more or less is changed and transferred to the fear. And considering the negative feelings or the fear or panic, so the state, the services, the society in general, in following hours and days depend on several aspects besides the visible rescue activities. It depends also on the level and quality of information which are provided both on one side to the rescue services and governmental or city agencies which are active in the field, and citizens in general. And we know also, we, so to say, are facing this worldwide. If proper information is lacking, then this information can take over and can cause additional problems which can become very severe. So proper information, fast information, which is reliable, is extremely important in case of such situations. And what are the people? Which informations are required? So, what are the questions which are raised both by citizens and the services? So, first of all, what and where has happened? Why has happened? what are the consequences of the occasion of the earthquake? So what are the humans? Are there human losses? Are people wounded? What is the level of material damages which were caused by earthquake? And I name it, what are the geo-related consequences? So in a sense, was there any displacement or, for example, destroyed roads? We remember, for example, when there was a strong, extremely strong earthquake in Japan, affecting also nuclear power plant in Fukushima. That geo-related aspect of the consequences of the earthquake was so important to for the Japanese government to come into the position to start organizing rescue and recovery activities, because many roads were damaged, many bridges were broken either by earthquake or by the tsunami which followed. So there was a lot of problem, and in this sense, all those occurrences I named geo-related consequences. Of course, also people want to know who is in charge. So who is organizing the rescue and recovery activities? Where can they get help if they need help? Where and how people can help to those who are affected by the earthquakes. So very many questions are raised. And today in the digital era, this is rather simple by using the tools of digital technology, communication technology. And I can say, for example, when Zagreb earthquake was happened, because the main Croatian telecommunication capacities are located in Zagreb, that telecommunications were out for several hours. But so to say, not too much so that this would affect rescue activities. So there was problem directly after the earthquake, but very soon those problems were removed, what is also very important. And then, for example, what has happened and what is our experiences. Some of you know, some don't know. So there is beside the national seismical service in Croatia. A lot of information were provided also by European Mediterranean Seismological Center, EMSC, which provides such overview maps of earthquakes worldwide. And on this picture, you can see the earthquakes which occurred in last 24 hours. Picture was taken this morning at 6 hours and 14 minutes. So you can see that there was a number of earthquakes on this zone, which is seismically active between the European and African plate. But why I'm using this example? The EMSC has enabled that citizens from the affected areas can provide to them testimonies and photos of the earthquake. And when the Zagreb and Petrinja earthquakes happened, and many earthquakes in days and months after those main strokes, people were so much communicating, so intensively communicated with EMSC, that this agency several times asked citizens of Croatia to stop sharing their informations because they basically blocked the web page, the portal of this agency. So showing how information is important in such situations to people, and how they are reacting on those on such situations. So if we speak about professional geosociety, as because it's not so easy to make uh, to distinguish who can contribute. So basically, I think geosociety is a correct word. So when we look in the questions which people are raising, some of them can be answered or responded by the geosociety. So for example, what and where has happened, why has happened. This is something what, in case of the earthquakes, geophysicists, seismologists are, so to say, people, professionals which are qualified to provide us answers. Same thing, for example, in volcanologists, in when there are volcanic eruptions, or some other professions in case of tsunamis or floodings or catastrophic fires, etc. So various, but it's known, so to say, who is asked to give answers, why something has happened, and what and where has happened. Another is a question is, what are the geo-related consequences? I, as a surveyor, will put surveyors to define them, so to say, but basically many professionals from society can, so to say, deliver information about geo-related consequences in case of earthquakes and other natural disasters. And then we have for the package, so to say, of issues or which are requiring information, and these are questions which we can generalize. Where can I get help, and where and how can I get help, provide help to those who need it? And this are again, geo and IT professionals are very qualified to not to provide informations, but to provide services, applications, which will enable both groups to start communicate and to exchange information and deliver help, support to those who need it. And I will show you two cases. It is, so to say, not a primary target of our training, but just to give to get so to say, overall pictures. So for example, when earthquake in Petrinja happened, and you remember that it was on 29th and 30th, 28th and 29th of December, already a day after the second strongest earthquake, the Faculty of Geodesy, together with the Croatian OpenStreetMap community and one company from this community called Openit, they established a platform, a digital interactive map with some standardized categories for easy input of supply and need for assistance in this earthquake threatened area. So you can see on this picture how this has looked like. So green are locations of people or groups of people offering help, and the red is basically people asking for support, looking for some goods, whatever. And it was very functional. It was very good. It was not, and you can look on this platform, on this address which I put here. It was not only one on the only platform which was established, but it was definitely a first which was functional and offered to the citizens to exchange the information. And it was very, very, so to say, beneficiary for the people, especially those who were in need after the earthquake. The second platform, which was established a little bit later, was a network application created again on the same platform, so together with the OpenStreetMap community, which was focused on assessment of the condition of roofing in the Banja, in this area which was affected. So basically, with usage of orthophotos, with usage of satellite images, and also usage of drones images which were flying over the Petrinja and other settlements immediately after immediately in days after the earthquake. A map of demolished roofs was created, which was also, so to say, a valuable information for the rescue services and other civil protection organizations to estimate the extension of the damages and the need of the citizens. This application was, of course, it was not so generally open application because it was serving certain purpose, but also very valuable to those services. For example, now we have a situation in this region that there is some over 2,500 containers delivered for people to have a roof under their heads so that they can live somewhere because their houses are unusable. And again, applications are created which are basically registering those containers and following what is happening with them, etc., etc. Another, and this is our focus of our interest, is the geo-related consequences. In this context, considering also what we faced in Zagreb and Petrinja earthquakes, is so our focus is on surface displacement. So what are the displacements in horizontal and vertical directions? Then are there any permanent displacements? So let me say, so a static displacement. And what were the kinematic surface displacements? So how did the surface behave during the earthquakes alone? And for this, we are using the satellite technologies, satellite systems, InSAR and GNSS. And in coming presentations, first Marian Grgic and then Daniel Sugar will present you, so to say, in short, those two technologies and demonstrate how the computations have been made and what are the results which have been achieved. At the very end of the training, we will also focus a little bit on the aspects of quality and aspects which are connected to the questions of sharing informations or what kind and which information can and should be shared in a sense of the quality of the information, reliability of computed results, etc. Because definitely the results of using those technologies should go into the direction to provide information to citizens and the services in a manner that they feel confidence, that they understand better what has happened and to to rely in the activities which are executed by the civil protection and all other services in the country. When we speak about InSAR technology, we have such sensors on many satellites, but here especially we are focused on Copernicus program because Copernicus program has a big advance since its data are freely available and almost immediately available. So in this sense, considering the fast response on the in case of the disasters, it is a very valuable contribution to the rescue and recovery activities. While considering GNSS satellite systems, we have several, so to say, possibilities for using this technology. So, for example, what we will demonstrate is the usage of coarse stations of permanent GNSS networks and what are the consequences to such networks in case of catastrophic earthquakes, which are also resulting in surface displacements. So these are the things which Daniel and Marian will share with you. And with this slide, I will finish the introduction to the training and stop sharing my screen. Just a second. Okay. And I will invite now Marian Grgic, a colleague of mine, to start his presentation. Marian, please, floor is yours.
Can you see me and hear me and see my presentation now?
We see you, but not yet your presentation.
Okay. Can you see it right now?
Wait. Yes.
And can you confirm that you just see the presenter mode, not the
yeah. Yes. So
okay. Okay, thank you, Professor Bacic, for the nice and extensive introduction to this important topic, which as you said during your presentation, is of a wide and global interest, not only for geodesists or Earth observation, but for geologists, sociologists, psychologists, and so on. So I'm going to be here with you today on discussing the fast disaster responses, especially using satellite technologies for surface displacement monitoring, and in general using satellite technologies or Earth observation for getting more data or giving more data, providing more data to the users when natural or human-induced phenomena such as the earthquakes or volcanoes or what is my research topic, my research interest, especially my research interest, sea level changes. So as Professor said, I'm an all-around player here using the Earth observations. My main focus is more onto the gravity deriving from satellite data using GRACE, GOCHE, or other satellite missions, and especially using satellite radar altimetry for sea level estimation, for deriving gravity models on the sea, and using those data to monitor the coast and how the sea level rises or sea level events impact or influence the coast. I'm postdoc here at the University of Zagreb Faculty of Geodesy, and we have, of course, different people doing different things here. I'm going to be sharing their research today as well. So our main focus today is to get some more information on the synthetic aperture radar technology or radar technology in general, and to combine it with different technologies. Later on, for example, in 45 minutes or 60 minutes, we're going to start using synthetic aperture radar data, or specifically Sentinel-1 Copernicus data. I'm gonna guide you through how to download data, which software to use for a quick delivery of the results, and what are the steps in processing synthetic aperture radar data. As you might know, or you are very familiar with, because we are from a different community or the same community, but with different pre-knowledge on the topic, synthetic aperture radar or radar technology came to its golden age right now. We have different, in fact, more than 15 spaceborne SAR sensors being operable today, and approximately 10 of the new synthetic aperture radar systems will be launched within the next 5 years. So we can say that using the SAR images will become even more popular, and we know that it is really popular right now. What are the benefits or main advantages of synthetic aperture radar comparing to multispectral, hyperspectral images? Synthetic aperture radar provides high resolution day and night and weather independent images for a multi-application ranging from geoscience and climate change research, environmental and earth system monitoring, 2D, 3D. We're going to focus today on a one-dimensional change, but during some period which can be referred to as 4D mapping, security-related application up to planetary exploration. The technology is here for more than 30 years. So starting in 1990s, with the advances in radar technology and geo-biophysical parameter inversion modeling, using data from several airborne and spaceborne systems became more popular, and some different and wide variety of the application in fact became popular and available. What is a radar system? It is a system that transmits electromagnetic pulses with high power and receives the which are transmitted from the satellite to the Earth's surface and backscattered from the surface. By analyzing the echoes of the backscatter signal in a sequential way, we can get the information on the Earth's surface. Typical values. So I'm going to emphasize that this system or these systems are active sensors which have their own energy that is transmitted from the satellite to the Earth's surface and sent back to the satellite system which analyzes the power returned and the wavelength of the returned signal, and in a process of processing the data give us some information on the Earth's surface. Typical values for the pulse repetition frequency range from a few hundred to a few thousand hertz. So we get few thousand information on the surface each second. The SWOT width, so the SWOT width that is monitored from one satellite varies typically from a few kilometers to 20 kilometers for the airborne case, and from 30 to 500 kilometers in the spaceborne case. Later on, we're going to focus on the Sentinel-1, and you'll see what are different products offered by Sentinel-1 and how to process them. The transmitted pulse interacts with the Earth's surface, and only a portion of it is backscattered to the receiver antenna, which can be the same as the transmit antenna. The amplitude of the phase of the backscatter signal depends on the physical, for example, geometry, roughness, and electrical properties of the imaged object, for example, permittivity. So depending on the frequency band, considerable penetration can occur so that the imaged objects and media must be modeled as a volume. For example, we have different frequencies that can go through the vegetation, ice and snow, dry soil, and so on. So different frequencies can be combined, or different, you'll see later, polarization of the signal can be used to analyze the surface as a volume. More penetration of the electromagnetic pulses in media will occur for radar systems using longer wavelengths, which can usually have an accentuated volume contribution in the scattered signal. So let's say that application of InSAR include geophysical monitorings of natural hazards such as the earthquakes, volcanoes, and landslides, which is important for us today. Then we have time series analysis of surface deformation. Again, it is in a way interesting for us today. So because earthquake can cause subsidence and structural differentiation of Earth's surface. Then again, we can use InSAR satellite aperture radar for glacier motion analysis. We can use it for digital elevation mapping. And on the slide, you can see that we can use, on a top left image, you can see that we can use synthetic aperture radar technology to monitor oil spills. Why is that? Because, of course, oil spills.
Dear Georgis, we cannot see another slide. In my computer, is still satellite system.
Okay, that is a slide. So these are the oil spills. So the basic. Okay, thank you for the information on that. So the oil spills have different properties of the backscattering the signal than the rest of the water, and you'll see later how it is consumed or used. You can easily define oil spills or detect it using radar systems. On a top right, you can see how you can you can see that one of the application of radar signal is for monitoring the ship transition lines or operational lines. You can monitor fires using SAR technology, or you can just monitor land cover. So let's take a look on the, for example, if you are referring to radar technology in general, you can refer to radar satellite altimetry. You can see schematic presentation here on the satellite altimeter, and you can refer to synthetic aperture radar data. And let's see what are the differences and how these systems can be integrated into one monitoring system. So for both InSAR or SAR satellites and satellite altimeter, you have a spaceborne technology or a satellite which is orbiting in a predefined orbit, and that orbit is monitored both by GNSS satellites, global navigation satellite system satellites, and from the terrestrial measurements such as the Doris Doppler measurements, which are also radar, which are also radio measurements, or satellite laser ranging measurements. So you can have the exact information on the position of the InSAR satellite, as well as the information on the satellite altimeter satellite. For both technologies, you have the radar instrument carried on the satellite that transmits the radar pulses through the atmosphere. That means through the ionosphere and troposphere. Ionosphere is, of course, hard to model and define. You have a signal that is propagating through the atmosphere, coming to the Earth's surface or water level surface, and backscattered. Some parts of it are backscattered to the satellite. With InSAR, we have incidence angle, or we have the angle that the angle that which is not 90 degrees. The same happens for the satellite altimeter, satellite radar altimeter. You have the incident level angle that gathers different types of measurements back to the InSAR instrument. When using satellite altimeter, in order to get the vertical land motion, you have to define. You have to, for example, if you have that situation, and later on you'll see one study we performed recently on how to estimate vertical land movement from satellite altimeter and tide gauge measurements. And let's say that tide gauge measurements or Mara graphs are the instruments set along the sea, along the coastline, which are measuring the sea. Same happens for the satellite altimeters. And by comparing the sea level trends or sea level state gathered from tide gauge and from satellite altimeter, we can establish estimation of vertical land displacements. Why is that? Because tide gauge measurements integrate the vertical land displacement because they are installed along the sea. So all the measurements integrate the vertical land displacements. And the satellite altimeter is not related to the land, it is related to the Earth center. So the trends and sea level we get from satellite altimeter is completely isolated from vertical land displacements. When you combine or compare tide gauge measurements to satellite altimeter, you can have the vertical land displacement evaluation. Another way of getting the vertical land displacement is by GNSS measurements. Daniel will elaborate on. And it is quite obvious that using the GNSS stations that are directly measuring vertical land displacements, you can have only point data there. And on top of that, you have InSAR measurements or satellite synthetic aperture radar measurements or interferometry from radar data onto the land, where you can get the surface land displacements. Comparing all three technologies, I'm going to show you in a few minutes. So all of the radar data are dependent on the satellite orbits. We have different satellites, different orbits, and different information gathered from different bands and different frequencies from each satellite. So, for example, when we compared JSON2, CRYOSAT2, and SARAL Altica satellite radar altimeters, you can have a good or great coverage on a sea. However, radar satellite altimeters do not cover inland, so you cannot really have monitoring of the sea level or water level inland, except largest lakes and so on, using radar satellite altimetry. Approximately at the same time, radar technology came into synthetic aperture radar technology and, of course, the radar satellite altimetry. So later on, you'll see that ERS and NVSat satellites carried both satellite altimeters and synthetic aperture radars. Different satellites enable different measurements. Today, we have both more than 5 or 6 satellites that are providing data regarding the radar satellite altimetry, and we have more than 5 satellite technologies or satellite missions providing synthetic aperture radar data. One of the events that is being monitored by radar technology, both synthetic aperture radar and synthetic aperture radar satellite altimetry, are the sea level changes. Later on, I'm going to show you a quick study on that. But let's say that we're using the radar data, pulse limited or SAR data, we can detect how the sea level rise affects the coastline. We detected in Croatia different parts of, or not just in Croatia, of Eastern Adriatic Sea that is being very much influenced by sea level change and is being expected to be flooded or near the floods, flood events within this century or within the next few decades. All those data are usually combined with a digital elevation modeling. If we are going for the best data or the most reliable one, we usually use drone measurements for monitoring the sea level. This example of combining radar data and the digital elevation model derived from drone mapping was done for the Krapanj, the island of Krapanj, near the Šibenik area in Croatia. So we detected that by the end of the century, if we expect, and we do expect, the sea level rise of approximately up to 1 meter, but different studies estimate different values, which are expected to be around 60 centimeters. You can see that some parts of the island can be endangered. And let's start with radar satellite systems, or that are a focus of this research or this presentation today, which are synthetic aperture radar or the satellite synthetic aperture radar interferometry. It all started back in 1992 using the ERS-1 and ERS-2 satellite. Later on, it was improved by RadarSat, ENVISAT, and nowadays we do have ALOS data. Its second generation, RadarSat 2, also second generation. And what we are mostly focusing on, because Professor said already, Sentinel data, which are completely free of charge, available, and the community is getting bigger each day. So our focus today will be on the Sentinel-1 data, which is a part of the Copernicus space program, mostly led by a European Space Agency with other research groups and research institutions around the world involved. So let's focus on synthetic aperture radar, which is an imaging radar system mounted on a moving platform. Moving platform in this case can be aeroplane or a satellite system. So similarly to a conventional radar, electromagnetic waves are sequentially transmitted and the backscattered echoes are collected by the radar antenna. So we have some deformation of the signal, which is propagating through the atmosphere. Later on, we have to process the data, correct it for the, of course, for the influence of the atmospheric and geometric influences. In the case of synthetic aperture radar, the consecutive time of transmission reception translates into different position due to the platform movement. So we have that platform which is moving around, and that is very important because that produces that synthetic, not a real influence of the radar measurements. Later on, we'll come to that. An appropriate coherent combination of the received signals allows the construction of a virtual aperture that is much longer than the physical antenna length. So if we had the radar system which is mounted on a satellite, in order to get a great resolution or more or much information on the Earth's surface, we would have to produce the antenna which is 5 kilometers long. Of course, that is impossible to design, and therefore we have the moving platform which moves along the orbit line, and we simulate that large antenna by getting more information each second or through each second on the same point. By synthesizing the length of the antenna, we get better resolution with small antenna, with antenna large, 5 meters or so. So the basic attribute of SAR is the origin of its name, synthetic aperture, giving it the property of being an imaging radar. In the case of SAR, the radar image results from processing the raw data and represents a measure of the scene relativity. So we have the simulation of a great radar size, radar antenna size, and that is synthetic within this technology. The top right image shows why the measurement has to be provided from the angle. You can see if there would be no angle or looking angle or incident angle, different names are used for that angle. we would have exactly the same return measurements for most of the narrow or horizontal areas in the world, and we couldn't really establish interferometry there. We would have exactly the same measurements backscattered to the satellite, and doubling the measurements wouldn't give us exactly what we would need. When the angle is 25, for example, degrees, you have different points on the Earth's surface measured with different reflected or backscattered signal, and by that you can provide monitoring of the Earth's surface in a better way. Of course, when you have that incident angle or looking angle from the spacecraft or from the aeroplane, some parts of the world or some parts of the terrain will remain in the shadow. For example, if there would be some mountain parts of the areas which are covered or not seen by the aerospace system, the satellite system, would be unmeasured. So that incident angle can be referred to as off-nadir angle. So we have a satellite orbiting around the world, and we have two different orbits. All SAR lasers travel from North Pole towards the South Pole for half of their trajectory, as can be seen here, and vice versa. So we have that ascending or descending orbits. So let's just take a look at the SWOT, or the area covered within the measurements. We have the SWOT area of that is wide up to, for example, 500 kilometers, or that area or SWOT size is the area that is illuminated by the radar signal. Range direction, as it can be guessed by its name, is direction of the illumination of the antenna. And we have that slant range, which is the range from the antenna to the Earth's surface being monitored. Later on, you'll see that this site is referred to as line of sight, and that line of sight, that satellite interferometry, is mostly referred to as mostly giving us the results of sea level vertical land displacement in direction of line of sight. Okay, so this is comparing the pulse limited radar to what we call synthetic aperture radar. I'm going to ask you for a second. In the office beside me, there's something happening. I have to warn them. Okay, I'm back. So if we ask ourselves what is synthetic about synthetic aperture radar, the spatial resolution of radar data is directly related to the ratio of the sensor wavelength to the length of the sensor's antenna. For a given wavelength, the longer the antenna, the higher the spatial resolution. From a satellite in space operating at a wavelength of about 5 centimeters in a C-band radar, for example, in order to get the spatial resolution of 10 meters, you would need a radar antenna of about 4 kilometers long. An antenna of that size is not practically for a satellite sensor in space. So we have that synthetic aperture radar that analyzes many of the backscattered signals each second or each few seconds, when we get a few hundred or few thousand measurements on the same image or on the same spot on the Earth's surface, at the Earth's surface. And by that, we are synthesizing the antenna. So this is what we have later on, resolution of 20 meters instead of 5 kilometers, which is what we get. So because of the nadir angle I said earlier about, some of the areas would be in a shadow and some of the areas would be overlapping. Those areas that are on the mountain would be overlapped by thousands of measurements each second, because the angle is approximately 23 degrees. For those areas which are below some of the degrees of terrain slope, they wouldn't be available to see from a radar, so we would have them in the shadow. So the role of the frequency and the wavelength. Radar sensors utilize longer wavelengths at the centimeter to the meter scale, which gives it special properties such as the availability or ability to see through clouds or vegetation. The different wavelengths of synthetic aperture radar technologies are often referred to as bands, with lettered designations such as the X, C, L, and P. You probably have seen these before. Different bands are used for different purposes. Usually, for example, for biomass monitoring, we need a P band. For urban monitoring, the X band is the most common band. And for example, today we have L band pretty much as a common for using the satellite interferometry. The role of polarization of the signal. So radar can also connect signals in different polarizations by controlling the analyzed polarization in both the transmit and receive parts. Polarization refers to the orientation of the plane in which the transmitted electromagnetic wave oscillates. So we have different combinations of backscattered signal. For example, if it's transmitted in a vertical plane and received in a vertical plane, we refer to those measurements as double V measurements. If, for example, the horizontal polarization is indicated by the letter H, and the vertical polarization is indicated by letter V. The advantage of radar sensors is that signal polarization can be precisely controlled on both transmit and receive waves. Signal emitted in vertical and received in horizontal polarization will be indicated as VH. Alternatively, the signal that was emitted in horizontal and received in horizontal would be indicated as double H, by double H letters. Different polarization can improve our understanding of the surface volume. Some of the polarization are better for monitoring the rough surface. Some of those are better for monitoring the volume, double bounce, and so on. So by defining the application, we need to understand better polarization. For example, rough surface scattering is that is caused, for example, by bare soil or water, is mostly sensitive to double V scattering, volume scattering, for example, caused by leaves and branches, in general vegetation in the forest, is most sensitive to cross-polarized data like VH or HV. And for example, double bounce is caused by buildings or large trees or high trees, tree trunks or inundated vegetation, and is most sensitive to double H polarization. For example, strong scattering in double H indicates a predominance of double bounce scattering, while strong double V relates to rough surface scattering, and so on. More on that should be investigated when different applications are used or implemented. So the sensitivity of SAR measurements to forest structure are different. Different bands can be reflected from a top parts of the vegetation, or some parts, for example, in C-band. When using C-band, all the signal can be transmitted from the inside of the vegetation, and there are some different bands that can provide us better information on, for example, deriving digital terrain models, because they penetrate to the vegetation up to the soil level. So at the beginning, we get the SAR amplitude and SAR intensity levels, which are pretty much grainy. You can see on the left-hand side, grainy image of a SAR measurement. We can provide, and we do provide, better images and better information within the satellite processing. For example, multi-image reflectivity map can be derived from more than one SAR amplitude signal image. So let's get the basics on SAR images, or let's see the basics as given by different authors. Radar sees through clouds. All weather imaging is possible. You don't need illumination by the sun. You can image day and night. It doesn't really matter for the active sensors which are installed as a radar observation systems. Surface roughness and slopes control the strength of the backscatter image. We can process it to derive better information on the land surface. If we define some image, we can see what has been already stated, that some slopes facing away from satellites will be in a shadow, which means there was a slope larger than the off-nadir angle. That's why we didn't capture any information in a shadow. Of course, those measurements or such measurements should be masked out within the processing. Slopes facing toward satellite have bright backscatter, of course. Those slopes are illuminated multiple times. You have some overlapping, and the brighter the area is, the smaller the incident angle of the of the nadir angle was. Then we can find areas of vegetations that can be rough and have bright backscatter. Using the radar images, we can easily defined vegetation indices such as the NDVI or so on. And by using the radar images, we can easily monitor the crops, for example, vegetations for a whole year, none depending on the day of the night, time of the day or night, or the weather. Sedimentary drainages, for example, are comparatively smooth and have less backscattered. Of course, we do not analyze such images just by seeing them by naked eye. We, in fact, process them and sort them out or filter them out, depending on the idea we need. So such measurements, such radar measurements, can also enable an analysis, and that is the focus of today's or today's training, analysis method called interferometry or InSAR. SAR technology using different, so we have different measurements of the same spot of the Earth surface by the same radar or by the same incident angle or nearly the same incident angle. We can compare those images and get the interferometric information, or the interferometer, which shows us which part of the wavelength of the emitted signal was different comparing to the other image defined by the radar. So InSAR uses the phase information recorded by the sensor to measure the distance from the sensor to the target. So we have a sensor to the target. When at least two observations of the same target are made, the distance with additional geometric information from the sensor, we need those information to fine-tune our measurement and overlap them in a process we'll get later too. Those measurements can be used to measure changes in land surface topography. These measurements are very accurate, up to the centimeter level or millimeter level, and can be used to identify areas of deformation from events like volcanic eruptions and earthquakes. Okay, you later on, I'm going to show you the interferometer, and we'll be able to analyze that. So by using this equation, which is pretty much the straightforward equation that defines the change in the signal phase, where, of course, lambda is the wavelength, delta R is the displacements in the line of sight, so line of sight, and alpha in this equation is a phase shift due to the different atmospheric corrections at the time of the two radar acquisition. So we have different times which we should correct the data for, and we have different measurements. Those changes in the wavelength, or those small delta R here represented, can be transformed to millimeters or centimeters in order to establish the estimation on the changes of the Earth's surface. We have different bands and different wavelengths, so it's quite straightforward. The same thing happens for GNSS measurements, and we are, I guess, all of us are pretty much familiar with the technology of GNSS. We have different bands, and for example, by X band, we can monitor the precisely the changes of the Earth's surface up to the 3.1 centimeters. Of course, we can detect larger signal changes or larger vertical displacements, but with less accuracy and less reliability. So it's quite easy. Phase shift due to the ground motion. Once it is measured in wavelength that is ranging from a pi, minus pi to a pi. And later on, it should be transformed into the centimeters or linear measurements. So if we, for example, combine two phases, two-phase measurements of the same spot at a different time, for example, August 12, image A, and September 16, image B, and we combine them in a process, we can see that we can see the interferogram, which is the phase difference of two images. By this or in this interferogram, you can see that something occurred right here. Probably, I guess this is volcano that caused the lava to change the vertical land around it, and you can see this fringes around or lines of different vertical displacement that are caused by the lava. And at this point, you can see that something happened, and you cannot really put the legend here and say this movement was 12 centimeters. You cannot really do that. You need the process of unwrapping the phases and transforming the phase measurements to the centimeters or to the meters. We'll come back to it later. So different interferograms are produced for different events, human-induced events or natural events such as the earthquakes. In this image, you can see the interferogram from Sentinel-1 SAR data, something like that. That is our goal for today or tomorrow. Sentinel-1 SAR data acquired during the 2018 and later on after the earthquake. And we can see that the interferogram shows earthquake fault slip on a subduction thrust fault causing up to 40 centimeters of uplift. We don't have that legend here, but we'll believe them that they produce the color scale for this image, but something like that will produce as well, and we'll see how those data are reliable or not. So let's see the another interferogram with the color scale beside. These measurements are again of the earthquake, which was a small one, in fact, or not the largest one. You can see that by the maximum and minimum displacement values, which are up to 3 centimeters or so. So not really a large deformation. However, those data we will produce today, for example, with, I guess, no issues. I did the pre-processing and went through the processing line or processing steps, got some interferogram you'll see are not 100% reliable, and those should be estimated regarding the accuracy, regarding the reliability. And that is why, because interferogram integrates the topographic effects due to the different elevation angles of the images. Those angles are pretty much the same, but not exactly the same. Then again, you have different atmospheric effects, which are accounted for in the processing data, in the data processing, but not completely. And you have true or real displacements you are looking for. However, there are some noises, measurement noises, systematic effects of the instrument that can vary through the time, and there are some outliers you cannot really predict or remove within the processing. So different research groups produce different results. Starting from 1990s, we have really different idea on what is going on prior and after the natural or human induced phenomena. And let's now see how those InSAR data can be implemented for vertical land motion. For example, if you are looking for a vertical displacement along the sea, I'm going to show you our study in Dubrovnik, which would be related to the topic today if the earthquake occurred near that area. Luckily, it wasn't the case. Unfortunately, it happened somewhere else. So we can go for the vertical displacements. I elaborated on in the introduction, using the differences of cell altimetry and tide gauge measurements of a sea. We can have the GNSS direct vertical land motion measurements. Daniel will elaborate on tomorrow, and we can have the surface monitoring of the land displacements from InSAR. We took the area of Dubrovnik, known for the earthquakes, smaller earthquakes prior to these earthquakes that occurred in Croatia last year. So that area is probably the area where Arabian or African African plate meets Adriatic plate or something like that. We are not completely sure whether there is the Adriatic plate which is completely not certain at the moment. However, this area is known for a lot of smaller and larger earthquakes from 1990s or 1900s, and even there are some ideas on the earthquake occurs back in the 17th, 16th century and prior to that. So we took that area, took the cell altimetry, tide gauge data, defined the differences, estimated the vertical land motion. We took the GNSS daily solutions, estimated the trends, again, estimated the vertical land motion, and we took the InSAR Sentinel-1 data. We pre-processed those data, 73 data images from 2015 to 2020. We formatted the interferograms or derived the interferograms of all the cases, corrected all the images, and produced the vertical motion from InSAR Sentinel-1. When we take a look at those measurements, you can see that later in the study, we get the information which is pretty much consistent from all of the three measurements. So from satellite interferometry or InSAR measurements, we get the surface area vertical displacements, which vary from 0 to -5 or -4 millimeters per year. From GNSS measurements, we get approximately 2 millimeters of the subsidence a year. And from comparison of cell altimetry and tide gauges, tide gauge that is installed in Dubrovnik area, marked here, we get approximately the same vertical displacements, which confirms our theory. So this is one of the ideas of using InSAR measurements. Of course, if you want to elaborate more on that, we have special guest topic in remote sensing, and feel free to come back to me later if you would like to publish your research related to cell altimetry or radar altimetry and its application in geodesy that includes InSAR measurements if they are related to radar altimetry. So let's make the introduction on the hands-on the Sentinel-1. So Sentinel-1, Copernicus Sentinel-1 is the satellite that orbits in a low orbit LEO satellite, low orbiting, low Earth orbit satellite, and it has a constellation of 2 polar orbiting satellites. Polar orbiting is a standard for SAR satellites, operating day and night, of course, performing C-band synthetic aperture radar imaging. That in fact means that the wavelength or the basic changes of the Earth surface are monitored with a wavelength of 5.5 centimeters. We have different polarizations, of course, and different elevation angles, which are varying from 20 to 46 in our areas that of nadir angle or elevation angle or incidence angle is something like 23. Antenna size is 12 meters by 1 meter, and the other specifics are listed below. Pulse repetition frequency is up to 3000 hertz or 3000 measurements a second, and these things are programmable. You can change it from a ground station. So the orbit type is, of course, sun-synchronous near polar circular orbit at a height of approximately circular orbit at a height of 693 kilometers. We have 6 days repeat cycle when considering both satellites, and for some areas I'm going to show you later on that. And we have different observation methods ranging from strip map mode up to the wave mode, which differs from the for the area covered and the spatial resolution. For example, strip map mode acquires data with an 80 kilometer SWAT at slightly better than 5 by 5 meter spatial resolution of a single look. The ground SWAT is illuminated by a continuous sequence of pulses, while the antenna beam is pointing to a fixed azimuth angle and an approximately fixed off nadir angle that can be subject to small variation because of the roll steering known for the satellites. Strip map images have continuous long track image quality at an approximately constant incident angle. Then we have interferometric wide SWAT mode, which is the main acquisition mode over land. We're going to use that mode today, and that mode satisfies the majority of service requirements. It acquires data with a 250 kilometer SWAT at 5 by 20 meter spatial resolution of a single look. Interferometric wide mode captures 3 sub-SWAT using terrain observation with progressive scans. You'll see later that the first step in processing of the data will be choosing the sub-SWAT, in that case, sub-SWAT is the second one. With the TOPSAR technique, in addition to steering the beam in the range as in ScanSAR, the beam is also electronically steered from backward to forward in the azimuth direction for each burst, avoiding scalloping and resulting in homogeneous image quality throughout the SWAT. So we have one image of interferometric wide has 3 different SWATs, and each SWAT has 9 bursts integrated in that. If we are going for a smaller area, we can define smaller burst size, or choose some bursts of a subswot of the interferometric wide SWOT image. So from 4 gigabytes of image, we can have a few hundred megabytes or even less. So similarly to the interferometric wide SWOT, we have the extra wide SWOT mode, which employs the top-star technique to acquire data over a wider area for, of course, using the 5 sub-SWOTs. Extra wide SWOT mode acquires data over 400 kilometers. And we are getting, by that technology, 20 by 40 meters spatial resolution. It covers a lot, you can see in the image. However, it doesn't really provide high spatial resolution. And finally, we have a Sentinel-1 wave mode, which is similar to ERS and NVSAT wave mode imaging, but with improved spatial resolution, larger vignettes, and a leapfrog acquisition patterns, as illustrated in the figure below, or figure there. So in order to ensure continuation of the measurements from 1990s, when NVSAT and ERS started their process, InSAR Sentinel-1 Copernicus satellite integrates the same technology, however, with some improvements and improved spatial resolution. When we start using Sentinel-1, we are offered different products. Those products depend on the acquisition type we saw on the slide before. There is a level 1 data, which includes noise, internal calibration, and eco-source packets, as well as orbit and attitude information. Usually we don't start with the level 1, except we are scientists interested in improving the data processing. Usually we start with level 1, which are focus data corrected for some things that have to be processed in order to use the product. The processing steps, those processing steps involve or include pre-processing, Doppler-centered estimation, single-look complex focusing, and image and post-processing for generation of single-look complex products or GRD products, as well as mode-specific processing for assembling of multiple sub-SWOT products. Level 2 products consist of geolocated geophysical products derived from level 1 and derived from level 1, in fact. So there are some ready-to-use products, such as the wind speed calculations based on the level 1 products you can see on the right-hand side. In order to establish interferogram, we have to use single-look complex products that have spatial resolution that depend on acquisition mode. In the table below, which is here, we can see different modes. I said earlier, we're going to use interferometric wide SWOT, which is this one, and the resolution depends on a different mode. Here you can see the statistics or specifics of that angle, of that mode. So Sentinel-1, as I said earlier, has some areas of the interest, of course, as it is focused on Europe and its usage in Europe mostly. And of course, some parts of the Antarctica, because lately we are focusing on monitoring what's going on with ice sheets on the Antarctica and Greenland, of course. We have a repetition period in Europe of 6 days. Usual frequency of the other measurements around the globe is 12 days. Such numbers can vary, and there are some situations where we don't have exactly the expected number of data, expected number of data there, but in fact, we usually have many data sets on each point around the globe. Okay, this is a mistake. Lapsus calami. Data download. We're gonna when we start using the Sentinel-1 data, we're gonna start with data download using the Copernicus Open Access Hub, and I'm gonna show you some other side that can be of a better value for your research. So we're going to look for the single look complex product that enable interferometry, because it encompasses both amplitude and phase information. You're going to see the data are completely free of charge, but asks for the free registration. So the practical assignment is to detect or process and provide interferogram for prior, comparing the prior and after the earthquake situation, or we are looking for the vertical displacements caused by the earthquake that occurred in Petrinja on December 29 in 2020. That earthquake, I'm going to remember you, was of the magnitude 6.4 or 6.2, depending on the magnitude scales. It caused some vertical displacements. Later on, we'll see what were the exact amounts of the influences. Such interferograms were made or have been made at our university before for Zagreb earthquake. For example, this one's from Marin Govorchin's public profile, public profile on Facebook, where he established interferogram of the Zagreb earthquake back in March 2020. So this is the final product we are looking for. We're not going to come to this exact product in our training, but we'll come to something like this that Olga made for the same area for the Petrinja in 2020 or the beginning of 2021, where you can see that displacements vary from at rates of the approximately half a meter. So how we're gonna use the data? We're gonna download single look complex data or image before and after the earthquake. Then we're gonna go to the pre-processing processes, processing steps, and at some point, correct means step in Croatian will define vertical and motion time series. We're not going to go be using MATLAB. This is from our research, which was extended research that lasted for a few months for another case, but will come somewhere in between, because some parts of the steps in pre-processing and processing will be switched and will not use stamps, which is a software or code developed at Stanford University for vertical displacements monitoring. Will use everything that is integrated in Snap. So it's 11 right now. I would suggest to make a small stop of 15 minutes, and we can continue with hands-on Sentinel-1 data at 11:20, if you agree with me. So I'm going to repeat that. We'll stop and we'll make a pause until 11:20, and at 11:20 we'll continue with our hands-on. We'll really start using Snap and start downloading data with the intention of deriving interferogram and vertical displacements. Thank you very much. Okay, it's 11:20 now, and I propose that we continue with our InSAR training by focusing on the hands-on Sentinel-1, meaning that in the next couple of minutes or an hour, we're gonna go to the data download using the Copernicus Open Access Hub. We're gonna go to the using the software which is ready to deliver interferograms using different Sentinel-1 inputs, and we're gonna get more familiar with the processing steps, processing techniques, and so on. So on a slide, you can see that a casual or usual or standard processing consists of reading different images. For example, there can be two images, one prior to the event of the volcano eruption or earthquake, and one after the event that can be also a human-induced event that has to be splitted or that has to be split or not. But if you split the scene or you crop the scene, there is a lot less processing there. I said earlier we're going to use interferometric wide SWOT, which covers 250 kilometers SWOT width, which means that each image has a really lot of information, and usually we do not need all the information. So we have the input being two Sentinel-1 images that have to be orbit corrected, and then there are processing steps in back geocoding, making the interferogram, the bursting, filtering, if that's what we wish to do, unwrapping the phase and making our measurement understandable or related to the centimeters, meters scales. By the end of this training, which will be tomorrow in the morning, we'll have the interferogram prior or which is analysis after the or was the event of Petronia earthquake. For all the steps, we didn't invent any of the steps. All the steps are available in a Sentinel toolbox tutorial. All different steps in processing are available on a YouTube. Different people provide different steps. So this is not a complete cookbook. This is a trial and error process where you process the data and define what you fit, what your idea of getting the results fits the most, or what if you have the control ground points, you can calibrate your measurements in order to provide better measurements with the InSAR. So let's start with the download of the data using the regular internet browser. We can access the Copernicus Open Access Hub. So this Open Access Hub is a great starting point for satellite interferometry, as well as the satellite multispectral analysis or hyperspectral analysis, everything related to the SNAP, which is a software for processing the Sentinel data, or Sentinel Toolbox software. Everything that is related to Copernicus satellite missions and beyond that. So there is a link at the site to the Open Hub. You have also different APIs without GUI, without graphical user interfaces. If you are more of a tech guy, or if you are processing a few hundreds of images, or at least tens of them. Beside the link to the Open Access Hub, you have different tutorials available in the information on new satellite missions and so on. So Sci-Hub, or Sentinel Copernicus Open Access Hub, is a place where you can register for free, and each time you have to, or you want to download the data, you need to log in yourself. It is completely free of charge, and a quick procedure that you can use to access the data. It's the best way to start looking for the images is to define the area you would like to make a research on or make a data on. And in this case, we are especially interested in Petrinja area, because the earthquake epicenter and hypocenter occurred in the area of city of Petrinja. So I'm going to mark using the right-hand side, right mouse click. I'm going to mark the bounding box of the data I would like to have the information on, and I'm going to look for the satellite data of the interest. So the earthquake occurred on December 29, 2020. So I would like to define the sensing period, for example, December of 2020. From December of 2020, let's say the first day of December, and we'll look for the images up to the end of the January. We are especially interested in Sentinel-1 data. Okay, different satellites we are not looking for the same satellite, although we could for different purposes. We are interested in single look complex data which integrate both intensity and the amplitude of the signal. Polarization, in this case, let's see what we can have. We tried estimating from different polarization, and similar results occur more or less for this purpose. So let's say let's look for this data. Sentinel Hub or Copernicus Open Access Hub will provide us data on that very soon. So you can see what I said earlier. Okay, let me draw that bounding box again. You can see here what I said earlier, that you will have some problems with width of the area, and some problems with a lot of data you will be getting. So you have really different images here, and you can really choose from all the inputs you have. And let's say that we can take a look at, for example, this image. Here you can see that this is IW, which is interferometric wide spot analysis data. The datum of the data is 11th of June in 2021, which is okay. We have some okay, it doesn't matter. So in general, you can really define each and any of these images you can take and make research on. Different ideas. You can have here. You can see a preview of that image for each and any of those. You have metadata for these images, and I guess images such as these images are okay for manipulating and defining vertical land displacements prior or after the earthquake. As this Copernicus Open Access Hub is pretty much a new thing or thing in development, you can see here that some bugs do exist here. So although we asked for in this case for the data from 2020 December up to the January 2021, we got a different data which are not completely from those dates. You can definitely look for all the images and find one you prefer to. Another way of getting the data is using the ASF Alaska University Institute for getting the data. And although I shouldn't suggest you that, I would suggest you just to explore the possibilities. I can tell you that you will certainly be able to download data of the interest from Copernicus Open Access Hub. Alternatively, you can look for the data using the bounding box again of the area using the Alaska Educational Institute. And here you can see that, for example, this image here shown here in a red bounding box covers the area entirely. When you mark it, let's find it. So when I mark it, it's from 4th of January in 2021. And it seems legit for us because that is the image after the earthquake. And if we look for the image prior to that happening or event, happening is too strong a word, event of the earthquake, we can see that we have almost exactly the same image from December 23, almost completely exactly. For example, you can see that this image would cover the same area, but we don't have a double image here. If we mark the image from 23 to 23rd of December, we have the image prior to the earthquake event, and the same image or almost exactly the same image of the same area using the same satellite can be in the same orbit, which is descending polarization W and V age. With these information available, then you know that we can really use these two images for making our interferogram. So I downloaded the data from this website. I checked here that there is exactly the same. So we can. This is exactly the same area covered later on in the same year, but there exists the same image here at the Copernicus Open Access Hub right now, and you will be able to find it. Although Copernicus Open Access Hub tries to minimize the uploaded data to their servers, so you cannot really download it right now. You put it in a cart, and later on they deliver it to you in an hour or two or in a day, depending on the busyness of their servers. So I preferred this one, and I have downloaded 2 of the images prior and after the earthquake event in advance. Those images are not small. Those images are approximately 4.5 gigabytes of the storage. So keep in mind that processing a lot of data asks for a lot of storage space. So when we download the data, we have 2 zip files which do have something integrated in it, but the best way to start with using the InSAR data or synthetic aperture radar data is just to take these zip files to the Snap software tool. Again, Snap Copernicus Sentinel download, for example. The Copernicus offers you the software for processing of the Sentinel data and the other data. And for example, if you are Windows oriented, you can download all the toolboxes regarding the Sentinel processing there, or different operating systems are also available for Snap download. So by downloading that software, which is approximately 1 gigabyte, you have the tool for processing the data. You start with downloading the data here, and you start processing the data in Snap for free, for example, during this training. So I said earlier, 2 images are more than 9 gigabytes of storage, and that's why I already opened all the data sets, or all the data sets that will be produced in our training during next 25 minutes. So these 2 files are the input files, or those 4.5 gigabytes images of the area here. And we can start by taking a look at the metadata of each image. You can see here that there are some different information on our image. There is information on the time, or on the different positions gathered from different sensors. You can see information in Doppler monitoring, satellite laser monitoring of the location. You can see the nadir angle. You can see, and so many different other things there. You can see the information on the bands and their polarization. Of course, their time interval, which is rather small, of course, in seconds, because as you heard already, we can vary the ingestion time or observation time up to the 3,000 images or information per second. So all of these information can be interesting if you are looking for the improvement of the processing things. If you are here for this training, I guess we will not deal with improvement of the metadata usage. Instead, you will probably come to using the bands you got here, and you will probably start using and processing things before you really take a look at all those metadata. So once you open the bands, you can see different things around. There are some IQ and intensity information. You can see that IV stands here for interferometric wide SWOT, and which has the SWOT width of 250 kilometers and resolution of 5.5 times 20 meters. You can see that something that is divided into IQ and intensity, and we use single complex SLC data because they consist of the complex imagery with amplitude and phase, and there is systematic distribution limited to specific relevant areas. So digital processing allows these pixels to manifest phase information as well as magnitude information corresponding to complex values. That is why SLC is a single look complex. So those complex values means that each pixel in the image is a complex number. Such pixel values require description with two independent components, such as a real and imaginary components, also known as in phase or I, and quadrature phase Q part or component, or perhaps magnitude and a phase component of the image. So let's take a look at the input image here. And as I said earlier, you remember that I said that each image consists of different number of SWOTs and different number of bursts. So this image consists of 3 SWOTs, so 3 segments of the 9 bursts. And for this area of the coverage, we will see later, we'll ask for to split the image into the so 3 SWOTs, and you see that our area is leaning toward the middle SWOT, so IV2, IW2, and the area we are going to look more onto is within the in the middle of this image, or within that middle row of the image. So the information we get at the beginning doesn't really look very informative, I would say. If we can vary here brightness and contrast, and we'll still not see much or many data here. There are some areas which are more black. There are some areas which are not as black as of course, but these things do not really give us any information. Which means that we will have to process radar data in order to see something here, to find some information within the data. So first step, before we start, we need to take a look where our data is. We can rely on worldview data, and okay, now it's downloading in the background, and I'm not sure how quick it is, but usually all the images are already pre-geocoded, but not all the segments of the image are geocoded. So the information got from the metadata puts our image somewhere related to the Earth, but so you can see here latitude and longitude, but those latitudes and longitudes are not related to the real world using the geodetic reference frame. Instead, we have the information on the satellite at that point of capturing the data, and we'll process the data in order to put all those interferograms to the coordinates. So, okay, is there any question? Not sure if that was a question. Okay. If there is a question, you can also write it down, and I'm going to try to answer that. So this is the input data, and as I said earlier, let's have that main SWOTs or main parts of the image split into what we need. So when we take a look at the map, and I did that earlier, comparing the coordinates, I saw that we need the middle image of what we downloaded. You can see that here. We need the middle SWOT. We have 3 SWOTs, 1, 2, 3, and we need that middle one here. Operating in Snap Toolbox software is pretty much straightforward. For example, if we want to split data, we need the input data images here entitled 14 and 15, enumerated 14 and 15. We can use functions integrated into Radar Toolbox. So for splitting the data, we need a Radar Sentinel-1 TOPS toolbox that can perform Sentinel-1 TOPS split. Once we enter the process, we have the input or source data. Pretty much we navigate ourselves to the information, to our we navigate ourselves to where we put our data, and I put it into separate folder. I'm not gonna change it because that was already selected. So my input data, I marked it on the left hand side, was here as a source. The target product can be just extended for the split extension. I would suggest leaving what is suggested or what is the default value of a new data in this processing step. You can use different directories, of course, and you can later on, after you process it, you can open it in Snap. Of course, as I said earlier, we wanted the middle SWOT, meaning that I would suggest you, for this purpose, taking the interferometric wide SWOT second or the middle one from this image. Why this one is the first one? We know that the satellite, this is descending orbit, so satellite goes from the North Pole to the South Pole, and when doing that, his first sub-SWOT is the first one to its left and our right in this case. So I would say you can go for the second sub-SWOT, and you should choose one of the polarization or both. In this case, I would go for the vertical. So the signal was transmitted from the satellite in a vertical plane and received in the same plane. Okay, I'm not gonna run it now, although this process is a pretty much quick one. Lasts for a couple of minutes, depending on your processing machine. Some of the processes are really time consuming. Also within this training, some of the processes would last for a couple of hours on your or my machine. So I did that prior to this training. So I'm gonna close this right now, but I would run it if needed, if I didn't do the processing in advance. So if we take a look at the first step, that was the read the file, split the file. Now we need to apply orbit file. Okay, so again, all the toolboxes that are related to the Sentinel-1 are listed under the radar toolbox title. And if you want to apply orbit file, you can just start searching for it. Of course, this one's the first one. You go for the apply orbit file, and again you have the source product. Now it's the source that has a split attached to the initial file. So that one is the one that is smaller, and the second slot was selected. The target product gets the extension of ORB or orbit file. You easily can define the processing parameters and so on. I tried different polynomials degrees, didn't make any influence, but of course precise Sentinel orbits or ephemeris should be used in this processing. So again, I'm not going to run it, but I'm going to show what you get after the after you do the processing. Let's see what we have right now. We have only the second subslot here, and we're going to use it for further processing. So let's see what can be our second step or next step. After applying orbiting file, we need to combine those two files. I didn't show you that I processed the first image same way I did for the second one, but you have to do that the same process for each image. Once you applied orbit files for both of them, you should go and do the co-registration, or not literally, but let's say some kind of overlapping two images in order to get those images overlapped, and so that you can make the interferogram out of that. So let's say that we need to perform co-registration now. We're gonna go again to radar co-registration, and we can choose from different types of co-registration, the back geocoding as suggested by different tutorials and myself as well. So in back geocoding, we need to process previously corrected for the orbit both images. So let's say that we want to add already opened images. So we need those two images that are corrected for orbit. You can see them right here. And we should look for both of them right here. So we need two of these. But back geocoding is a process that co-registrates two images using their information given in metadata and the information given in by the digital terrain model. So my suggestion is always to use until we get something better, SRTM 1 second grid, which probably is the best digital terrain model already, although it is 20 years old right now. So I would suggest you to correct the data using the SRTM grid selection. And before you run the process, if you are not familiar with the process exactly, and you found this process somewhere online, I would suggest you to use help integrated in the snap, because it is really informative and you get some better insight onto what you are doing. So, for example, there we can see that back geocoding is co-registering two SLC split products. You see that split products have to be the same, and of the same subspot, of course. That is the step we made at the first step of our processing. And in resampling the save images into master frame, there are some steps that are to be performed. As said here, and as you probably know, some global elevation models or the digital terrain models have different accuracies or precision. Maybe in your country, in our country, SRTM usually outperforms the other. If you have information on other things, you can use different specifics there. Bilinear interpolation seems enough for me, but you can go by for bicubic interpolation, of course. When you are doing bilinear interpolation, you take a look at only 4 points around your desired point. We're using the bicubic interpolation. You put 16 points in that computations, and that can cause some time-consuming processes which you don't really need, or you're not completely forced to do. Again, you will have that product as an output of this image. I'm not going to run it, of course, because it's too time-consuming. But once you do that, you will get the extension stack, which means that your two images are stacked one to each other. Again, we'll try to take a look at it. Keep in mind that the processing is pretty much slow. Now you can already see some things are going on there. Maybe if you improve the brightness. Okay, when you improve the brightness, you will or change the brightness, you will see some things that are very visible in radar data, such as the river and water areas. Those areas have higher reflectance and, of course, can be better seen on the image. So the next step is getting the interferogram, and after that we'll make a pause until tomorrow. Let's see how we can make that interferogram we talked about in the presentation. You can see here crops, different crops, very obviously a very apparent line around the river. So let's say that we need the, okay, we can prior to going to make that interferogram, we can enhance spectral diversity by using radar. Just a second. Just a second. Okay, that would be the next step. I would suggest you to enhance spectral diversity so that the image is more clear, but that is not the main step in this processing. You can go without it, but I would suggest you to go with it. Again, it is pretty much straightforward. There are some processing parameters I didn't vary, but those types of processing improve what we see in the image. Then there is making the interferogram out of that stacked image. So it's again pretty much straightforward. Radar, interferometric, products, interferogram formation. Once you click on that, you need the source product, which is the enhanced spectral diversity thing you pre-processed earlier. You get that there some pre-processing parameters. I would suggest you to go for subtract flat Earth phase, of course, because of the Earth flattening. You should correct for that because you're looking for millimeters or centimeters. Again, there is a subtract topographic phase. I would go for that, and I do go for that. I take a SRTM 1 second grid to correct for the data, and once I run it, yeah, usually I get interferogram. And let's say what we get there. Okay. Interferogram. Let's see the phase of the interferogram we produced. We see that the interferogram varies or ranges from -pi up to the +pi. So we have only the wavelength from minus to plus, from 1 pi to -1 pi to 1 + pi. And this image is referred to as interferogram. However, we don't see anything, or we cannot really make any conclusion when we see that things vary regarding the wavelengths. Tomorrow in the morning at 9 a.m. we'll start with this image, and we'll transform this image, which shows the phase amplitudes of vertical land displacements. And you can probably see that the earthquake happened somewhere here, but we cannot really claim that. We'll transform this image from the phase measurements, -pi, 2 pi, into meters, and we'll see what really happened. I'm gonna give you a sneak peek on what happened there. Let's say that let's see displacements. Okay, we'll probably do some better image presentation, but you can see that the variation of displacements is up to 13 centimeters or 0.13 meters in a plus, and you can see that it's somewhere at -10 to 20 centimeters in a minus. So if we take the statistics, displacements occurred after the earthquake were from 14 centimeters up to 35 centimeters in plus. but let's say that we'll come to that later on today. And let's see that we came to this step, and that step is somewhere here, making the interferogram. Now we have some different steps and some other different steps in order to get it done. So I'm going to stop right now. Thank you for the attention. I'm going to leave all the questions because we somehow broke the time limit. I'm going to leave the questions for the morning. You can prepare yourself. You can download the snap data. You can download the data again, or you can download the data of our earthquake or whatever earthquake you would like to analyze, and we'll define vertical land displacements tomorrow in detail. Okay, there is one question from Raquel. Is it possible to have this recording? I guess it is. It is not up to me, but we do record this meeting, and I don't see why wouldn't you have more information on processing the data afterwards, and you will be able to download the recording. Okay, so you are welcome to join us tomorrow for getting to the end of this InSAR analysis. We'll have that interferogram unwrapped into the meters, and you'll see what happened really there. If we'll have some time, and I guess I'm going to try to do that, we'll show that in a QGIS or any GIS software, and hope you will get more information on that, maybe get more interested into using technology. Thank you very much, and goodbye until tomorrow. Bye-bye.